Hi, let us today discuss the Dirichlet's theorem and the Dirichlet's conditions. This is an important theorem connected with the Fourier series, and it discusses the convergence of a function. We are expressing a function f of x as a Fourier series, as an infinite sum of sines and cosines. That is what we do in Fourier series. And how does it converge? That is given by the Dirichlet's theorem. We are not proving it, we are just stating the theorem. The theorem is like this. If f of x is periodic, well defined, bounded in the interval minus pi to pi, and it has only a finite number of maxima and minima, and has only a finite number of discontinuities. Okay, these are the conditions to be satisfied when if we have to express a function, a periodic function, in the form of Fourier series. Okay, so f of x is periodic, well defined, bounded in the interval, and has only finite number of maximum minima, and has only finite number of discontinuities. Then the Fourier series for any value of x converges to this f of x plus f of x minus at every value of x. Okay, at every value of x it converges to this value. So this is what Dirichlet's theorem is stating. Okay, so we see a function f of x plotted here. This is actually okay, periodic, it's satisfying all these conditions. At any value of x, it converges to this half of f x plus and f of x minus. Okay, so this is what the Dirichlet's theorem is telling us. Here, at these points, the function is continuous. Okay, at all these points, the function is continuous, but at x equal to x0, it is discontinuous. At points where it is continuous, what this means is the function will be converging to f of x, simply f of x. What is the value of f of x? And f of x plus means you are, coming to this point from here. And f of x minus means you are coming to this point from here. Okay, and they converge at the same point for the values of x for which the function is continuous. So, at all these points, it is converging to the value of f of x. The problem comes at the point of discontinuity. See here, for this value of x, this is discontinuous, because if you are coming from here, or if you are coming from this value of x, it converges to this point. Okay, but if you are coming from here, the function steadily increases and comes to this point. And at the value of x0, we cannot say what is the value of f of x. It may be, if you are coming from right, it will be taking this value. If you are coming from left, it will be taking this value. So at this point of discontinuity, we can clearly say it converges to this at the point of discontinuity here. At x0, it converges to the half of the value when you are coming from right, and you are approaching from right, f of x0, when you are approaching from right, f of x0 minus, if you are approaching from left and you take the sum and take the half of it, it will be converging to this value at the point of discontinuity. Okay, you can always expect discontinuity in the function that we expand. At continuous point, there is no problem, because f of x plus x0 plus, that will be equal to f of x0 minus f of x. Okay, because if you approach from left or right, you will be coming to the same point. So if you take half of this, you will be getting f of x itself, f of x plus f of x minus half, you will be getting f of x itself. So it converges to f of x. So at continuous points, at the points where the function is continuous, then there is no problem, nothing to worry. But at the point of discontinuity, as we shown here, this is the point of discontinuity at x0. There is a vertical jump in the function. There it will be converging to the middle or the half of the f of x plus and f of x minus. So this is what the Dirichlet's theorem is telling us. Okay, and Dirichlet's conditions are nothing but what we show in the Dirichlet's theorem. The conditions imposed on f of x, the theorem are called Dirichlet's conditions. What is it? The function must be well defined and bounded in the interval, as we said in the theorem. The function must be continuous or piecewise continuous. That is, the function may have only finite number of discontinuities and only finite number of maxima and minima, that we know, and the function must be periodic. So all these things that we have said in the theorem, and that is separately written as the Dirichlet's conditions. Okay, so Dirichlet's theorem deals with the convergence of the Fourier series, where the Fourier series is going to converge. Okay, at continuous points, no problem. You know, it converges to f of x, the value of f of x at x. But at the point of discontinuity, it converges to this. Okay, it converges to this value, half of f of x plus half of x minus. Okay, so it's a very simple theorem to understand. And let's do a problem, general problem, connected with the Fourier series. Suppose that we have a function of period 2 pi such that f of x is 1 for value of x in between minus pi and 0 and 0 for value of x in between 0 and pi. Okay, this is the function with us. And we sketch a graph of f of x in the interval. And what we have to do is we have to sketch a graph of f of x in the interval minus 2 pi to 2 pi. And we have to show that the Fourier series, in this case, that is given by half minus 2 by pi sin x plus sin 3x by 3 sin 5x by 5. Okay. Now we have to, by giving an appropriate value to x, we have to show that pi by 4 equal to 1 minus 1 by 3 plus 1 by 5 minus 1 by 7. Okay. That by putting appropriate value to the x, we will show that pi by 4 is this. Okay. So the first thing that we do is we are sketching the function. We know for x in between minus pi and 0, its value of x is 1. And for x in between 0 and pi, the value is 0. So we have this, we are sketching this. So its value is 0 and here it's 1. Okay. And we do the, and since this is periodic, we just extend this to minus 2 pi, the same thing. 0 to 2 pi it is like this, and since this is periodic, we can expand only periodic functions as Fourier series. So we, kind of, this will be the sketch of the function. Now let's see the Fourier series expansion. A0, we have to find A0, AN and Bn. So A0 is given by this. Okay, 1 by 2 pi integral minus pi to pi f of x dx. We substitute over here, we split it into two integrals. So minus pi to 0 f of x dx, then 0 to pi f of x dx, and minus pi to 0 f of x dx. Okay, minus pi to 0 f of x dx, what is its value? Its value is this. Okay, 1. This is actually minus pi to 0, its value is 1. And 0 to pi, its value is 0. So that we give here. Okay, and we get the 1 by 2 pi, 0 plus pi, that is half. An is given by 1 by pi minus pi to pi f of x cos n x. And we know for minus pi to pi, we have 1. Sorry, minus pi to 0, we have 1. For 0 to pi, it is 0. So we need to consider only this interval. So we integrate, and as we integrate, cos n x, as we integrate, we will be getting sin n x by n. And we apply the values, the limits 0 and minus pi. When you put 0, it will be 0. And when you put minus pi, you will have sin minus n pi. And sin minus n pi is minus sin n pi. So that minus and this minus will cancel, or it will become positive. So 1 by n pi sin n pi. Now the thing is, sin n pi is 0 for any integral value of n. Sin n pi is 0. So this will be 0. So we are getting an as equal to 0. A0 we got as half. The next step is finding the Bn. Bn, the formula is this. Once again, we need to consider only the interval minus pi to 0, because for 0 to pi, this is 0. F of x is 0. So we have this, and we integrate, and we have minus cos n x by n. We apply the limit minus pi to 0. And here, when you apply 0, you will have minus 1 by n. And when you apply minus pi, you will have, cos n pi. Because cos minus n pi is cos n pi itself, because cos is an even function. So plus cos n pi by n. And minus 1 by n pi, 1 minus cos n pi, if you are taking minus 1 by n pi as, common factor. So cos n pi is minus 1 to the power n. Okay, cos n pi is minus 1 to the power n. So that we give. So for odd values of n, Bn is minus 2 by n pi, and for even values, this is 0. Okay. For odd values, this is minus 2 by n pi. For even values, this is 0. So f of x is equal to, f of x is a0 plus sigma n equal to 1 to infinity I n cos n x plus sigma n equal to 1 to infinity b n sin n x. Okay, so f of x that is given by half, a0 is half. And if you put n equal to, 1 to, an is 0. So we need not consider this. We need to consider only this part. So we have half Bn. Bn is minus 2 by n pi for n odd. For n even, it is Bn is also 0. So we need to consider only odd values of n. So this is f of x is equal to half minus 2 pi by sin x minus 2 by 3 pi sin 3x minus 2 by 5 pi sin 5x. Half minus 2 by pi, this is sin x, sin 3x by 3, sin 5x by 5, okay, etc. like this. So this is f of x. We have got the Fourier series expansion of f of x. See, f of x contains a sum of sin function, sin x, sin 3x, sin 5x like this. So if you add, what this means is if you add half and then minus 2 by pi, then sum of the sin x. Sin x, you know, it will be varying like this, or similarly sin 3x, that will be varying like this with a period 1 by third of this. Then sin 5x. If you add all this, we are getting the f of x. So this is what the Fourier series is telling us. Okay. So we have this. Then if you put x equal to pi by 2. Okay, you are putting x equal to pi by 2. The value of x equal to pi by 2, at that point the function is continuous. See, here comes pi by 2. Here the function is continuous and its value is 0. So this is given by 0 equal to half minus 2 by pi 1 minus. When you put x equal to pi by 2, here you will be getting 1. Here you will be getting minus 1 because you will have sin 3 pi by 2, and for sin 5 pi by 2 you will be getting 1. Okay, so you will be getting this 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 like this in final series. Okay, and if you rearrange the terms, half taken here 2 by pi, and this will give pi by 4 as equal to this. So you are finding the value of pi by 4. So at x equal to pi by 2, the function is continuous. At that point, the value of f of x, that is equal to 0. Okay. Now at x equal to pi, at x equal to pi, the function is discontinuous. See, here the function is discontinuous. Why? If you are approaching from the right, the value is 1. But if you are approaching from left, its value is 0. Okay, so this is 1. We have f of pi as equal to half of f of pi plus, then plus f of pi minus. F of pi plus is 0, f of pi minus is 1. Okay. So f of pi, that is equal to half f of pi at the point of value of pi. It's kind of 0, and when you are coming from here it's 1. So 1 plus 0 by 2. Okay, we have to use this. This is 1 and this is 0. So 1 plus 0 plus 1 by 2. Yes, 0 plus 1 by 2, so that will be equal to half. This is actually f of pi plus. Pi plus is 1. Okay, f of pi plus is 1. This is 0. So we have 1 plus 0 by 2, that is equal to half. So in the equation, if you put x equal to pi, naturally this will be 0. See, sin pi, sin 3 pi, sin 5 pi, all these are 0. So this becomes 0. So f of x you are getting as half. And by the Dirichlet's theorem as well, you are getting the same value. Okay. What you are getting at the point of discontinuity by Dirichlet's theorem, it's half. This one is also giving you, if you put x equal to pi, this one is also giving you half. So that's correct. Dirichlet's theorem, that's the correct one. This is how you apply the Dirichlet's theorem to the series, to the Fourier series. Okay, and you can expect discontinuities and continuities. Okay, So let's stop.